All right, people are starting to come into this session. Hi there, Pratyush. Thank you very much for joining us. So previously we had Eduardo from Protocol Labs talking about a zk circuit for Lark language, and now we've got Pratyush, chief scientist over at Aleo, ready to talk about Arkworks. I'll let you take it over.
Awesome. Hi, everyone. Very happy to be here, and thanks for the opportunity to talk about Arkworks. So I think everybody can hear me, right?
Yes.
Okay, awesome. So then I'll start. Okay, yeah, so in this presentation, I'll be talking about Arkworks, which is a Rust ecosystem for zkSNARKs. And I guess Arkworks, I am a co-maintainer of it, but it's the hard work of a lot of contributors, of which I'll try to list all of them towards the end. Yeah, you can find our GitHub repo at this link, arkworks.rs. Okay, so I talked about what is Arkworks, but why do we need Arkworks, right? So let's take a look at what it takes to develop an application that uses zero knowledge, and specifically zkSNARKs, right? So today, if you want to develop an application that uses zero knowledge in a non-trivial way, the first step that you have to think about is how you can express your computation or your problem in a language that the SNARK understands, right? And the issue here is that there's many languages and many frameworks for doing this today, right? You have Leo, Socrates, Noir, basically any number of languages and DSLs and various techniques for writing or expressing your problem in a way that the SNARK understands, because the SNARK doesn't usually out of the box understand a language like Python. Okay, so this is step one. After you've done this, depending on which path you chose, right, you might have to further make a choice of which zkSNARK is sufficient and sort of works for your use case, right? There's many options here. You might want to go with like a trusted setup, circuit-specific trusted setup application. I mean, maybe application is okay with a circuit-specific trusted setup, in which case you can use Graph 16. Maybe you'll need something which has universal setups such as Plonk or Marlin. Maybe you want transparent setup, and you should go with Halo 2, and so on and so forth, right? Okay, so now let's say you've done that. You still have to figure out what underlying algebraic object you want to instantiate your zkSNARK and your computation with, right? So maybe you want to use the BLS 12381 curve. Maybe you want to use the pasta curves for recursion. Already in this talk, we've seen, various choices that you can make on all of these dimensions, right? And finally, once you've done all of this, you still have to implement and optimize your algebraic object, but also, maybe each of the intermediate steps, right? And there's many different choices, again, to make here. So overall, basically, it's like this seemingly never-ending sequence of things when all you wanted to do was just to use zk in a cool way for your application to maybe implement better privacy. All right. So, okay, in the face of this, how are people developing applications which use zkSNARKs today, right? Unfortunately, usually what happens is that people, they bring on an experienced cryptographer, and the cryptographer decides to implement or try to implement parts or maybe each portion from scratch, right? This results in a bunch of libraries such as CirCom, GNARK, libsnark, the various iterations of Bellman, each of which are individually, quite good, but they're all duplicating effort, right? And so why does this happen? Well, each library might have its own set of optimizations, which are known to the authors of that library, right? Furthermore, there's sort of new techniques and algorithms every few months. So you might find it easier to just implement this optimization in your own library versus trying to upstream it in somebody else's library. And it also needs to interface well with the language that the rest of your code base is using. Okay. These are all good reasons, but they also come with certain problems. So the first problem is that this leads to a ton of wasted reimplementation effort, right? So all these optimizations just scattered across different libraries, they are not shared. So maybe if we combined all the optimizations from all the libraries in one place, then you'd get possibly the fastest SNARK provers out there, right? Okay, so furthermore, sort of upgrading becomes difficult, right? Maybe CIRCOM doesn't interface well, for example, with Halo 2, right? So how do you upgrade from Groth 16, which is what CIRCOM initially uses, to Halo 2 if you want a transparent setup, right? And finally, going back to the point of basic implementation effort, also auditing and bug fixing efforts are sort of split across all these libraries, right? So attention is scattered across these places. And so a bug which is fixed in CIRCOM might not necessarily be fixed in GNARK and vice versa, right? And not to pick on CIRCOM on GNARK, I mean, they're like excellent code bases, but just the other point is that attention is split across the two or across the entire ecosystem. So how do we overcome these issues? And the idea would be to sort of make it easy and low cost to focus all our effort on one set of libraries, or one ecosystem of libraries, and make it easy to reuse that library across various use cases, right? So to achieve this, we need our ecosystem of libraries to be modular. It should be easy to mix and match components and easily swap out outdated techniques for newer ones. It should be ergonomic to use library, right? It should not be like a real pain to write a secure application by default, right? And finally, it should be easy to get high performance, right? To get good performance, right? Even if you have good ergonomics, you should not be sacrificing efficiency, because at the end of the day, sort of that's what can make or break your application. All right, and that's basically what we try to do in Arkworks. So we try to construct a modular, ergonomic, and efficient Rust ecosystem for zkSNARK programming, right? So from a modularity perspective, we leverage the Rust type system in Arkworks to abstract away details and offer reusable interfaces at each level of the stack. And this is how we sort of, allow people to swap in and out components easily, swap out elliptic curves, swap out SNARKs, and so on, as we'll see later in the talk. From an ergonomics perspective, right, we again use the Rust type system to encapsulate implementation details and offer secure defaults, right? So by default, you're doing the correct thing. Furthermore, we can leverage sort of the low-level, in some sense, nature of Rust to allow embedding within other languages, other libraries easily. Okay. And next, from an efficiency perspective, again, we're able to use the low-level nature of Rust to sort of offer, despite this modular and high-level implementation or high-level interface, we're able to offer efficient, sort of state-of-the-art assembly or intrinsic implementations of, for example, field and curve arithmetic, as well as high-level algorithms such as MSMs and FFTs. Okay. So let's take a look into how sort of we achieve this at each level of the stack. So at a high level, sort of Arkworks consists of a few different types of libraries that all work together. At the lowest level, we have the libraries which implement the basic algebraic routines, such as elliptic curve arithmetic, finite field arithmetic, polynomial arithmetic, and so on, right? We encapsulate all of these behind some generic interfaces, so that you don't have to worry about the implementation details of your elliptic curve. Above this sort of generic algebraic interface, we provide a sort of generic interfaces for zkSNARKs and constraint programming, and implement proof systems that leverage these interfaces, right? And we have quite a few libraries here, such as Groth 16, Marlin, generic polynomial commitment libraries, and so forth, and so on and so forth. Okay, then above this layer, we sort of use these zkSNARKs and sort of the generic interface for SNARKs to implement sort of high-level gadgets or computations in sort of R1CS, for example, right? So we provide R1CS, sort of a standard library consisting of R1CS gadgets for integer operations, finite field operations, elliptic curve operations, and use these to in turn implement things like collision-resistant hash functions, signatures, Merkle trees, and so on. Finally, sort of leveraging all of these interfaces below, we're able to construct applications which are sort of generic in terms of the underlying components, such as an implementation of a privacy-preserving smart contract system like zkSNARK, generic proof carrying data, which sort of links up with the previous talk which you just saw, right? So all of these top level applications are generic in terms of the underlying components, and you can switch out, for example, the SNARK very easily in our implementation of zkSNARK. Okay, all right. So now let's take a look at sort of maybe some pieces from each level of the stack and see how we achieve our goals of modularity, ergonomics, and efficiency. Starting with the bottom of the stack. Okay. So when focusing on, let's quickly recap why we need algebra. So basically every zkSNARK that you use requires an implementation of efficient finite field arithmetic and usually polynomial arithmetic, as well as oftentimes elliptic curves, right? So at this level of the stack, what we want from any library that provides these operations is that it should be easy to implement a new field or curve and also, optimize this implementation. But we don't want to sort of duplicate effort, right? Like if somebody's already implemented, short Weierstrass arithmetic, we don't want to have to re-implement that again and again. So let's take a look at how the Arkworks libraries achieve this goal, right? So in terms of ergonomics, let's list out. Let's take a sort of case study of implementing an elliptic curve. So in this task, we have to first implement the associated fields for the elliptic curve, such as the base field and the scalar field. And then we have to implement the curve itself, which involves specifying the coefficients of the curve and then specifying the cofactor and generator, basically the information which defines the elliptic curve. All right. Let's see how we can do all of these steps in Arkworks. So to implement the associated fields, this is basically, we'll take the example of the bn to 54 curve, right? So to implement the base field for the curve, we just specify what the modulus is, right? Specify the generator, and then, with a little bit more boilerplate, we're done. Same thing for the scalar field. We specify the modulus, the generator, and then a little bit of boilerplate, and we're done. This is all it takes to specify sort of the elliptic, the scalar fields, which define the G1 of the bn to 54 pairing friendly group. Okay, so how do we now implement the curve itself? Okay, so again, it requires just specifying what the base field and scalar field of the curve are. Then we specify the cofactor and some additional information. And finally, we specify the coefficients, which are just 0 and 3 in this case. And then we specify the generator, and then we're done. Basically, in this slide, in the previous code block, that's all it takes to specify in Arkworks a new elliptic curve, right? And you can see this in sort of recent PRs in our libraries, where again we implemented new curves like sec-p256k1 with just a few lines of code. Okay. So this simplicity of implementing new curves has allowed us in Arkworks to easily implement a lot of elliptic curves that are used sort of throughout the ecosystem, such as BLS12381, BN254, the pasta cycle, BLS12377, which are used by a bunch of projects in the space, as well as the MLT cycle. And now we also have implementations of the ED25519 set of curves, as well as sec-p256k1. Basically, it's becoming easier and easier to implement new curves in the Arkworks ecosystem, and any curve that you require, you can probably find it in our ecosystem. Okay. So now we have a bunch of these curves, but how easily can you actually switch between them if you need to, right? So let's say you started off with Grot16 to instantiate over the BN254 curve, but then you found out that BN254 is no longer secure, so you want to upgrade to the more secure BLS12381, right? So in Arkworks, doing this upgrade is as simple as a matter of just switching one type parameter. You can just switch out the BN254 type with the BLS12381 type, and then you're done. But okay, obviously your protocol needs some, needs to handle the switch at some point, right? But from the perspective of the proof system code, there's really nothing that needs to happen that's complicated. You just switch out this one type parameter and you're done, right? Same thing with simpler primitives like signatures. You're able to just switch out the underlying elliptic curve. Okay. Now, in terms of performance, we don't sacrifice efficiency to achieve these nice ergonomics and ease of implementation, right? Compared to sort of two extremes, one which is Bellman, which is sort of a pure Rust implementation, and the other is sort of MCL, which is like a state-of-the-art library which uses fancy techniques like dynamic code generation. Arkworks is able to achieve very competitive performance, in some cases beating MCL, and in sort of all cases being faster than the Bellman libraries, right? And obviously, I think there's been some efficiency improvements on all of these, but I think sort of the ballpark is still in this, so the difference is still in sort of this, the delta is still as on this page. Okay. All right, so sort of the takeaway is that we're able to implement at the lowest level of the stack. We're able to provide for all of modularity, ergonomics, and efficiency without sort of sacrificing any of these dimensions. Okay, so maybe let's move up quickly to the next level of the stack and focus on SNARKs and their implementations, right? So at this level of the stack, you care about an optimized performance. It should be, you should have a very fast SNARK, but it should also, not be like this convoluted mess that's difficult to follow. You want to be able to reference the math in your code very easily, right? Okay, so I think I only have 1 minute, so I'll go through this part very quickly. But basically, again, switching from a modularity perspective, our design makes it easy to switch between proof systems if you need to. So for example, if you want to switch from Groth16 to a non-malleable proof system such as Groth-17, it's a matter of changing one type parameter. And then if you want to upgrade to universal setup, again, just changing one type parameter essentially. And if you want to go to transparent setup, again, you can just change one type parameter. So basically, it's all very modular. At the level above, like at the level of programming circuits, none of this makes a difference. That's completely oblivious to this level of the stack. Okay. And also the code, as I said before, sort of matches very closely the actual mathematics, right? So these two steps, basically define the Groth16 verifier. And as you can see, the code implementing the verifier basically matches these steps exactly. Okay, so I don't think I'll have time to go over this portion, but basically the takeaway is that in our interface, we've made it very easy to sort of make writing constraint code look almost, make writing constraint code almost as easy as writing the native code. Here's one particular algorithm. We don't need to know which one it is, but as you can sort of just glance and see, the implementation of the constraint code looks almost exactly like the implementation of the native code. Okay. Okay, so the question is, okay, I've covered a bunch of stuff, but has any of this effort actually been useful? And the answer is yes. Our code base is used in a bunch of places, including Manta Network, right? And also in a bunch of academic research papers. And these companies have contributed back to the project also in various ways, which has been fantastic to see. And sort of some of these contributors are listed on this page. And sort of Arkworks is overall the joint effort of a lot of, I guess, very collaborative nature of the entire space. And it's been really exciting to see the libraries grow and sort of the space also grow. So that sort of wraps it up. To get involved, you can, I guess, interact with us at any of these links, or you can reach out to me to ask about, how to get started with Arkworks. Thank you.
All right. Thank you very much, Pratyush. That was a great presentation. And for those of you that didn't see in the comments, Shumlet has said that we learned a lot from Arkworks on how to build modular interfaces in Rust. So thank you very much for all the contributions that you've made, not just to Arkworks, but also, to helping us out with our own development. And so with that being said, thank you very much for your presentation, Pratyush. And we will move on to our final presentation for the first session, which will be with Bulwen. He is the co-founder and CTO at Hardware Acceleration for ZKP. And so I'll